audible and my screen is visible. Just started the recording. You can wait for a few minutes. The attendance is abysmally low. While we wait, in case you have any doubts, suggestions, anything, please feel free to let me know.
Sir, I have a doubt.
Go ahead.
Sir, in last class, you told about that equivalence class and the cycle and orbit. So in that the example that you had given
Mhm.
was the sigma means was sigma, and you had written equivalence class of only 3, 8, 7, and 1.
Have I even written?
Means you told equivalence class of only 3, 8, 7, and 1, and you told that it is a cycle,
3,
but
7, and 1. No, that doesn't make sense. So 3, 7, and 8, they remain as they were, right? There's
yes.
nothing happening to them.
Mm, yes.
So in fact, the cycle would be 1, 2, 6, 4, 5, and 1.
But sir, if there are means in all orbit, all list of orbit, uh, at most one orbit have more than one element. But here,
Mhm.
more than one orbit have more than one element.
So give me an example.
Like two, two, one, four. Equivalence class of two, equivalence class of four. They
But
both
they are
have
in the same equivalence class, right? 2 and 4 are in the same equivalence class.
yes.
But 1 goes to 2, 2 goes to 6, 6 goes to 4, 4 goes to 5, 5 goes to 1.
Hmm.
So all these elements are in the same equivalence class.
Okay, so there should be no repetition of elements.
Right, because we are doing a permutation. Permutation means bijection. So bijection means there cannot be any repeat.
Mm-hmm.
Sir, can you give an example of another pattern from
Sure,
this?
sure. Yes, so that is what we are going to start the class with. 80 students. Let's begin. Okay, so let us just, I had written all of this. I hope it's okay if I don't repeat all of this again, right? Do you want me to go through this again?
No, sir, just that equivalent.
Sure. So cycle. Okay. So proposition 9, right? It says that each permutation, okay? So it is talking about each and every. So each permutation sigma, right? It induces an equivalence class, equivalence relation on the set on which you are performing permutations, right? And the equivalence relation is defined as P is related to Q if by applying this permutation again and again, at some point you hit the element Q. Okay, if that happens, then P and Q are related. Okay, so if I take this particular example, sigma, okay, what are its equivalence classes? So let's find the equivalence class of the element that contains 1, or rather, let's find the equivalence class containing the element 1. So 1, right? We begin with 1. And if I apply sigma to 1, what element do I get?
Oh.
2. Okay, if I apply sigma to 2, so applying sigma to 2 is the same as applying sigma twice to 1, right?
Yes, sir.
Right. So what happens if I apply sigma to 2?
6.
6. Next,
4.
4, 5, and 1. So 1 is again here. So Need not write it again. So this is one equivalence class. What are the other equivalence classes? So 1, 2, we are done. Let's look at the element 3. What happens if I apply sigma to 3? I get 3 only, right? So no matter how many times you apply sigma to 3, you're going to get 3 only, and which is why the equivalence class of 3 is a singleton set. Okay, so 1, 2, 3, we are done with 4, 5, 6. What about 7? Again, it's a singleton set, and so is 8. Okay, these are all the equivalence classes of the set A, where the equivalence relation is induced by this permutation sigma. If you want, we can take another example. Give me any permutation that you want to look at, and we look at that case. So how many elements do you want the set A to contain?
8.
8. Okay. Give me the permutation now.
3 to 6.
3, 2, 6.
5, 4, 1, 8, 7.
So let's find the equivalence class that contains the element 1. What happens to 1 if I apply 5? I get 3, right?
Yes.
Then what happens if I apply 5 to 3? 6. What happens if I apply 5 to 6? Get the element 1 again, right? So 1 is already there, so that is all this equivalence class contains. Then equivalence class containing 2, because phi doesn't do anything to 2, the equivalence class of 2 contains only 2. 3 is already here, equivalence class of 4.
5.
4
4,
and
5.
5. Right? Again, if I apply 5 to 5, I get 4 again. So that is all. And 6 is already here. 7.
7, 8.
7, 8. So these are the 4 equivalence classes of A induced by this permutation phi. All right?
So this is not a cycle.
Exactly. Why? Because let's reread the definition of a cycle. A permutation sigma in SA is called a cycle if there is at most one orbit, okay, with more than one element. Okay, and if that happens, then the number of elements in that orbit is what is called the length of the cycle. So this is a cycle, sigma, whereas phi is not a cycle. Is that clear?
Yes, sir.
Yes, sir.
So basically we have answered the question I was going to put next. So all cycles are permutations, but are all permutations cycles? The answer is
No, sir.
no. Right? Because we just saw an example of a permutation which was not a cycle. Okay. Now how do we denote a cycle? Right? This is a slightly cumbersome notation for permutations. This one. Right? In case we have a cycle, right, rather than any arbitrary permutation, then there is a simpler way to denote that particular permutation. Okay, so that simple way is you have been given a k cycle. Okay, k cycle means cycle of length k. We can denote it by just this k tuple, okay, I1, I2 to Ik, okay, where all of these elements are coming from the set A, okay, and these, this k elements of A, they are members of the largest orbit. Clear? And what is so special about writing it this way? I mean, what are these k elements? How are they related? So the relation is given here. If I apply sigma to the first element, I will get the next element. If I apply sigma to the second element, I will get the third element, and so on and so forth. The penultimate element, if I apply sigma on it, I will get the last element, and if I apply sigma on the last element, I will get back the first element. Okay, so maybe we can take this example. This sigma is a cycle. How do we denote it? Anyone?
One,
Next.
2, 6, 4, 5.
That's it. Okay, so instead of writing what sigma does to all 8 elements, if sigma is a cycle, then we just have to denote its largest orbit in a particular order. Right? So this is not a set notation. Right? Please understand this carefully. They are ordered in a very specific way. Okay, so given the element 1, if I apply sigma to it, I get 2. On 2, if I apply sigma, I get 6. Next 4, 5, back to 1. Of course, there is nothing that says that you need to pick the smallest element first. Okay, so you could as well start by, let's say, the element 4. Okay, so 4, when I apply sigma, I get 5, 1, 2, and 6. These are equivalent ways of denoting that particular cycle. All right? Does that make sense? Okay,
Yes, sir.
Okay. Right. So another question for you guys. So we have already proved that the set of permutations on a set A, right, is closed under function composition. Okay, but how about cycles? If I take 2 random cycles, right, of course on the same set, right? Remember, cycles are also permutations on a particular set. So consider a particular set and take 2 cycles in random. Okay, I can then compose these cycles also, because these cycles are nothing but permutations. Okay, so technical term used for composition of cycles is product of cycles. Okay, this is how usually books will refer to it. So what do you think? Will cycles be closed under product or composition? One. Maybe let's take examples. Okay, so these are 2 cycles that you can see on the slide. Remember, this notation is basically saying that, let's say this cycle denotes a permutation sigma, and this cycle denotes a permutation phi. This is basically phi composed with sigma. So what would be the resultant permutation, right? Will it also be a cycle? Can we find that out? So maybe let's work this example out so that all of you are comfortable. So I'm assuming A has only 6 elements. Even if it has more, it doesn't really matter. Right. So remember, since these are permutations, so therefore they are functions. So we are going to use the left to right rule. Okay, we'll first apply, sorry, right to left rule. Okay, we'll first apply the permutation of the function that is given on the extreme right, and then we'll move to the left. Okay, so can you tell me Where does sigma map 1 to, and so on and so forth?
Sigma maps 1.
Sorry? 1, where does 1 go?
Sir, is map 2.
Itself.
Yes,
Itself.
sir. Itself. No, nothing in top cycle.
Good. Then 2,
3,
3. 3,
4,
4. 4,
6,
6. 6,
2.
2.
2. Right? Remember, the last element maps to the first element.
Yes.
And what about 5?
Itself.
Itself. Good. Then, how about 5? What does 5 do to 1?
3,
3. 3 to
5,
5. 5 to
1.
1.
1. How about 2, 4, and 6?
Itself only.
Itself. Can you figure out if this function, right, is a cycle or not?
So yeah, 2 should be mapped to itself in 5.
Once again,
In 5, 2 should be mapped to itself.
my voice is breaking, so I'm not able to understand your question, Nilesh.
Yes, sir, it is a cycle.
If it is a cycle, then what is the cycle notation?
1, 3, 4, 6, 2, 5.
2, 5. Right, so it is a cycle, right? There is no element left out anyways. But is this in general true? Right? That's the question. An example doesn't prove anything. Let's look at an example. Let's say this is sigma, this is pi. Okay, quickly, sigma. 1 goes to
1.
itself.
1. 2 goes to
5,
5. 5 goes to 6.
6,
6 goes to 2. Okay. 3, 4. We remain as it is. How about 5? 1 goes to 2.
2,
2 goes to
4,
4. 4 goes to
6,
6. 6 goes to
1,
1. How about 5 and 3? Remain as it is. Is this mapping a cycle?
No.
no,
Right? And sort of see 1 goes to 2, 2 goes to 5, 5 goes to 1. Okay, 3 remains there. 4 goes to 6, 6 goes to 4, 4 goes to 6 again. So there are 2 orbits containing more than one element. Therefore, I compose with sigma is not a cycle. So what is the conclusion?
composition of cycles is not cycle.
Cycles are not closed.
Okay, great. Let's do another example. How about this? Third one. And give you a hint, you don't need to write down anything. Just stare at this, you should be able to figure out what will happen. Will it be a cycle? Again, the hint is you don't need to write anything.
No, sir, it is not cycle.
Why?
It contains two equivalence classes of more than one element.
No. So my question is the composition of these two permutations, right? So if I call this as sigma, this as phi, the composition of this two permutations, will it be a cycle or not? And you're saying not a cycle, so I'm just asking why.
Sir, it contains two equivalence classes which are of more than one element. So it is not cycle. Composition of
So exactly. So the point is not sigma and phi, but the composition of these two permutations itself will contain two orbits with greater than one element. And that you can see just from the way the cycles are composed, right? There is basically no intersection between this and this. And there are no elements common. So there is no way in which any element from this particular cycle is going to enter here, and there is no way in which elements from this permutation are going to enter here. Okay? These are what are called disjoint cycles. Okay, which is not the case with the first two examples. Right? And in the first two examples, we saw that the resultant of these two cycles, either it could be a cycle or not, writing that cycle notation would be slightly difficult. You will have to sort of figure out how to do it. But as far as you have disjoint cycles, right, there is no other way in which you can simplify apart from just reordering the elements in the same cycle. The only other way is, would the order matter? Is this equality true?
Yes, sir.
Right? The order doesn't matter as far as your cycles are disjoint. Okay? So we are in fact going to prove this. Okay? Just to give you the definition, two cycles are said to be disjoint if their largest orbits are disjoint sets. Okay, so I hope the definition is clear. So let's first write or look at the proof of this proposition. Okay, so disjoint cycles are going to be important. Before I give you what is the importance of disjoint cycle, let us sort of prove this result. It says that any permutation of a finite set, okay, can be written as a product of disjoint cycles. Okay. So by the way, remember there are several ways in which you can write permutations. Okay. First example and the second example, they show that you can write a permutation as cycles which are not disjoint as well. Okay, but what we are now saying is any permutation of a finite set can be written as a product of disjoint cycles. Okay, is the statement understood?
yes, sir.
And so if that is clear, how will we prove this? From proposition 9, what do we have?
Equivalent.
Equivalence relation or orbits, right? So sigma induces equivalence classes, okay, or what we also now call orbits. What is special about orbits or equivalence classes? Anyone? What is special? What is the property of an equivalence class? Can there be any intersection between the equivalence classes?
Sir, equivalence partition the set.
No, sir.
Nilesh, once again, your voice is breaking.
Sir, I'm saying that the equivalence class partitions the set.
Partitions the set. So, in other words, there is no intersection between any two equivalence classes, and all elements belong to one equivalence class, right? So,
Yes.
let O1, 2, and OP be the orbits of sigma. Okay, let's write this down that OI intersection OJ is an empty set for all ij from 1 to p, and union of all these orbits is going to give you. Then what? I want to write this sigma, this permutation, as a product of disjoint cycles. So I already have a partition of A, right? So using that partition of A, I can define a cycle, isn't it? So what I can do is define, let's say, tau I, okay, as tau I applied to A, right, gives me sigma applied to A if A is in the ith orbit. Okay, and otherwise, if A is not in the ith orbit, then just keep it fixed. Okay, so then I hope it is clear that sigma would be nothing but tau I composed with tau 2 composed with tau. Make sense? Each of these tau I is a cycle, right?
Sir, each of tau I contains one orbit and all other elements are
Fixed.
mapped
Exactly.
to itself.
Yes.
Okay, sir.
So see, there are p orbits, right?
Yes, sir. So
So
there
for
will be
each of the
T
p
cycle.
cycles,
Okay.
exactly. And I hope it is clear that why these p cycles should be disjoint. Simply because the orbits are disjoint.
Yes, sir. Clear.
Anybody who did not understand this? Anyone? Doubts with this?
Sir, I didn't understand this.
Okay, so in specific, where is the issue?
I mean, these define tau I.
Fine. Okay. So tau I, right? I'm going to define p permutations. Okay, 1 to p. Okay. How am I defining these p permutations? So tau 1. Let's take I equals 1. Okay. Now, if in order to define a permutation, I need to define what it does on each and every element of A, right?
Yes.
Right. So now there are two choices for A's, right? A either can be in the ith orbit, or since we are taking I equals 1, so either A is in orbit 1 or it is not in orbit 1, right? There is no other choice.
Hmm.
If it is in orbit 1, then I'm defining this permutation equal to, right, tau I maps A exactly to the same element that sigma maps A to,
Hmm.
right? So
Yes.
sigma is already given to us, right? So this is a well-defined permutation. Okay, and where will sigma map A to?
Tau I.
No, but in specific. So what is the property of
Orbit.
the orbit? Exactly. So sigma A or tau I A, right? If A is in the ith orbit, will map A to the same orbit, but a different element.
Hmm.
Okay. The other possibility is this element A may not be in the ith orbit. In that case, I am leaving A as it is. I'm not doing anything to it.
Okay.
So is tau I, so the first question is tau I a cycle?
Yes, sir.
Yes, Swandan, I know you understood. Let the person who had a doubt, right, let me ask him. Is it clear? Would tau I be a cycle?
Yeah.
Think, I
Yes,
mean,
sir.
it's okay.
Yes.
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 Why?
Sir, because tau I either consists of one element or more than one element, and all are disjoint. Not disjoint.
No.
Sorry. Uh, it contains some common element, I think.
See, tau I will change, right? Will map A to a different element only if A is in one particular orbit, right? For every other element, tau I will do nothing to A. Okay, so therefore, what is a cycle? It's a permutation whose at most one orbit contains more than one element.
Hmm.
Okay, so for tau I, OI will be the orbit that contains at most, sorry,
One.
OI will be the orbit that contains more than one element. Okay, so that is why tau I is a cycle. Yes.
But sir, tau I will contain more than one element, but it will also contain one element because
No,
of.
no, no. See, tau I is a function, so doesn't make sense to say it will contain more than one element. What do you mean by that?
Hmm.
See, sigma A will be different from A. Okay, and then all elements of the ith orbit.
Okay, will contain sigma I.
No, so by applying sigma or tau I again and again, you are going to get all elements of OI.
Of I,
Right?
yes.
Okay, so that is the largest orbit, which may contain more than one element. For every other element which is not in the ith orbit, tau I is doing nothing.
Yes.
So that is why tau I would be a cycle.
Okay.
Yes.
Yes.
I hope you honestly mean that you understood.
Yes.
Then the other thing, I hope the last line here is understood, because again, these OIs, they partition the set A, right? And the way we have defined tau I, only one tau I will have any impact on A. Rest all taus will not do anything to A. Understood? Only one tau I can do something to a particular element A. And it will be the tau I for which A is in the ith orbit. Make sense? If you guys want a couple of minutes to sort of understand this, it's okay. I can give you 2 minutes. You can think about this. And then once you are convinced, let me know. Otherwise, if you have doubts, please ask. Try to clarify these two things. One, each of these tau I is a cycle. That's the first thing. And the second, I believe, is relatively easier to see that sigma is a composition of tau 1 to tau p, and tau 1 to tau p are disjoint cycles. They are disjoint simply because they are defined on a partition of A. So I hope that should be easy to understand. The only challenge possibly is to see why these tau I are cycle. Can we go ahead?
I'm having a doubt over here.
Go ahead, Nilesh. Maybe you can type your doubt because I'm unable to hear you clearly. Nilesh, I hope you're typing. Are you there, Nilesh? The product two cycles. So, okay. Basically, the composition of functions. So, do you want me to repeat this example? I can show this thing. Okay, so let's take this second example, right? So these cycles, please remember, is nothing but a commutation, right? A special kind of commutation. And commutations are nothing but functions, bijective functions. Therefore, product of cycles is nothing but doing composition of two functions. Okay, and we follow the convention of functions where if I have to compose two functions, I start from the rightmost function and then slowly proceed towards the left. Okay, so in this example, we start with the permutation sigma. Okay, what does sigma do? Apart from 2, 5, 6, all elements they remain as they were. Okay, so 1 goes to 1. 1 goes to 1, 3 goes to 3, 4 goes to 4. Okay, what happens to 2? 2 goes to 5, 5 goes to 6, 6 goes to 2. Okay, so 2 goes to 5, 5 goes to 6, and 6 goes to 2. Right now, as happens in function composition, the second function will operate on the result of the first function. Okay, so this row over here is the result of the first function. So we should start from this, not from this row. Okay, so what does phi do? Phi is this cycle. So it does nothing to 3 and 5. Okay, so 3 goes to 3 and where is 5? 5 goes to 5. Okay, that's the easy part. Next, what does phi do to 1? 1 goes to 2, 2 goes to 4, 4 goes to 6, 6 goes to 1. Okay, so 1 goes to 2, 2 goes to so composition of permutations. Okay, cycle is a special kind of permutation, and these representation, it just sort of reduces the space required for representing that permutation. Just think what will happen if you have to write permutations all the time in this notation. Right? That would be too cumbersome. Okay, so instead of using this notation, you have these special kind of permutations which are called cycles, and these cycles at least are easier to represent in this way. Just write the cycles, I mean, just write the orbits. Okay, so the tarang is fine. Any other questions, doubts?
Sir, can you give an example of this for permutation as product of disjoint cycle?
You want another example apart from this one? So this was an example of disjoint cycles, right? This one. Yeah. You can see the two cycles are disjoint, right?
Yes, sir.
So what do you want me to do? You want me to work it out?
No, sir. No, it's okay.
So there is
Right.
nothing to work it out here. That's what I'm trying to say. Because what this cycle does has nothing to do with what this cycle does. Right? So if this is sigma, if this is sigma and this is phi, right? What phi does is independent of what sigma does, simply because they are disjoint. So there is no way, I mean, if you want, we can work it out, but there is in principle nothing to work out. So, okay, let's work out phi. So what does phi do? Leaves 1 as it is, 3 as it is. 2 goes to 5, 4, 5 goes to 4, 4 goes to 6, and 6 goes to 2. That's your phi. What about sigma? Sigma only operates or permutes the element 1 and 3. So 1 goes to 3, 3 goes to 1, rest all they remain as they were. And if you look at the notation for this, it's of course not a cycle, but you can write it as a product of these two. There is no other way in which you can write this down. All right.
Yes, sir.
Okay. So let's go to the next proposition, proposition 11. As we sort of found out in that example, right, that these two cycles commuted. This is the same as 6 and 1, 3. Okay, and this is not only true for this specific example, it's true for any cycles as far as the cycles are disjoint. Fine. So how do we prove this? Let's just start with two arbitrary cycles. Sigma 1, sigma 2, permutations, which are disjoint cycles. Okay. Now, what can you say about the elements of the set A? Right. So let us also denote two disjoint cycles with orbits O1 and O2. What can we say about any element in A?
So either A will be in sigma 1 or sigma 2 or
Not sigma 1 or sigma 2. Please correct yourself.
orbit
Sigma
1.
1, sigma 2 are permutations, okay? They are not
Yes, sir.
sets. So,
Orbit 1 or orbit 2 or in neither.
right. So, for any element A in the set A, either A is in O1 or A is in O2 or A is in A minus O1 union O2. Right? These are the only three possibilities. And also, in this, I hope is clear. What is the intersection between O1 and O2?
5.
Right? It's an empty set. Why?
We consider
this-
them as a disjoint.
Right, because sigma 1, sigma 2 are disjoint cycles. Okay, so they have only one orbit each with number of elements more than one, and those two orbits cannot intersect. Okay, so if you sort of have that in mind, I think the proof is easy. So let's work out the three cases. Right, the first is, let's take the simplest case, A minus O1 union O2. What would sigma 2, sigma 1 applied on AB?
A itself.
A itself, and it would be the same as sigma 1 composed with sigma 2 applied on A.
A will.
Okay.
Yes.
What if A is in orbit 1? Then what would sigma 2 composed with sigma 1 applied to AB?
Sigma 1 of A.
Sigma 1 of A, right? And how about sigma 1 applied, sorry, sigma 1 composed with sigma 2 applied on A?
Sigma 1A.
Sigma 1A. Then similarly, you can work out the third case as well. Okay, so therefore, sigma 1 composed with sigma 2 is equal to sigma 2 composed with sigma 1. As far as sigma 1 and sigma 2 are disjoint cycles. Any doubts here?
No, sir.
Thank you. So now let's try to see what is the benefit of disjoint cycles. Right? We have obtained a few properties of disjoint cycles, right? That they commute, and secondly, any permutation of a finite set can be written as a product of disjoint cycles. What is it? I mean, yes, the proofs are clear. What is the importance, right? That is something which is not clear. So, for that, let's look at this question. Okay, so remember, we will always have the group which is the symmetry group of some set A, SA or Sn, in mind when we are answering this question. So, if A and B are two elements of an arbitrary group, okay, and let's say the order of the element A is P, the order of the element B is Q. What is the order of the element AB? I believe, I think there was a similar question in the last week's tutorial. Can you answer this?
So LCM of A, comma B. Or LCM of
Sure.
order of A, comma order of B.
Can you
Yes.
prove that?
Yes, sir.
How? So AB to the power K, what will this be equal to?
This, if K is order of AB, then AB raised to
No,
K will
fine,
be
but that's
identity.
okay. So that would be E, but let's say K is not the order, then. So let's just maybe take a small example. Instead of an arbitrary K, let's take AB to the power 2, simplest. What is this equal to?
AB dot AB. Yes, I got that. If it is follows to be
Different times.
commutative, then only we can say.
right?
If G is
So
abelian.
louder. Somebody who wanted to say something, I missed it. So once
If G is
again,
abelian, then AB whole raised to K should be A raised to K, B raised to K.
right. So if AB, so once again, remember we don't need to assume that G is abelian. Okay? As far as these two commute, if AB is equal to BA, then AB to the power K is equal to A to the power K, B to the power K. Need not talk of the entire group being abelian. Right? I hope you see this point.
Yes, sir.
Now, can you see what is the importance of disjoint cycles? So the group of permutations, right? Is it abelian? In general, do you think this is an abelian group? Of course, we didn't look at several examples here, but in general, what do you think? Anyone?
Sir, in general, it is not abelian because it is
Abelian?
not necessary to be disjoint cycles.
Right. Yes, so that's the simplest answer, right? As far as you have disjoint cycles, you can commute, but we have seen examples of permutations which are not disjoint cycles, right? And in general, of course, as far as number of elements in A is greater than 2, in general, this will not be abelian. You can try this out. I mean, take 3 elements. So the number of elements in SA would be 6. Right? So that is sort of the smallest non-abelian group size. Okay, so with 3 elements, you can work out all the permutations and see that it is not abelian. Right, so this is why this is the same case, right? So the entire group, which is SA in this case, is not abelian. But if you take any two disjoint cycles, then these two will commute, and therefore, what can we do? We can easily find out the order of AB. Okay, now what does proposition 10 tell us? So if I give you a permutation and I ask you to find its order, right? So as this particular result says, if AB do not commute, then it is going to be a very difficult task to find out the order. Simply because you cannot write this as A square B square. Okay? But if we can, if A and B commute, then computing the order of AB is easy. Okay, what does proposition 10 guarantee us?
That any permutation can be written as disjoint cycles.
Cycles. And any disjoint cycles, they commute, so therefore it is easy to find the order. Okay, so let's look at this example again. What is the order of a cycle? Can anybody tell me? Or maybe this in general. What is the order of this cycle, I1 to Ik?
Okay.
Okay, do you all of you agree?
Yes, sir.
Yes, sir.
I1 goes to I2, you again apply it, I1 will go to I3, so on and so forth. If you apply it k times, I1 will come back to itself. And so is the case for all other elements. So a k cycle has order k. Right? So computing the order of one cycle is easy. How about computing the order of a product of cycles? What is the order of this? The order of this is 4. The order of this is 2. What is the order of both of these?
4, sir.
4. Why? Because
LCM of 2, 4.
4 is 4. Okay. Hope you have understood this. Any doubts?
Sir, in a representation of cycles, you have written that sigma of ik is equals to I of k plus 1.
It is. Is that what I've written?
Yes, sir. Last line. Sir,
No.
here,
No, sigma of ik is I1, right? So I didn't write.
well, sir, not
sigma-
ik, general formula, I of j. Yes, sir.
Ah,
So, sir, there I of j plus 1 mod k should be there because it will
no,
not work for sigma of k.
no, but j takes values only from 1 to k minus 1, right?
Yes, sir. But for ik, we have to
So which
define
is,
other way.
yeah, so that is why I wrote this separately. The problem with modulo is you will get 0. And I don't have I0 here.
Oh, yes, sir.
Okay. I hope it is clear. Once again, there is no way in which I will know whether you have followed or not unless you tell me. Okay, now let's look at even more specific permutations. Okay, the permutation we'll focus on for the rest of the class and maybe even the next class is going to be 2 cycle. Okay, so what is a 2 cycle? The largest orbit contains only 2 elements. Everything else is remains fixed. Here, and 2 cycle is in general called a transposition. It exchanges the position of 2 elements only. That is what is a 2 cycle, and it's going to be referred to by the name transposition. So now we are going to prove is not only that any permutation can be written as a product of disjoint cycles, any permutation can be written as a product of only transpositions. Okay, so in some sense, what this tells us that every permutation can be seen as a series of exchange of 2 elements. Any permutation you give me, I can obtain that permutation by just exchanging 2 elements at a time. That is what this proposition means. How do I prove this? The proof is easy. Okay, so remember proposition 11 said that any permutation can be written as a product of disjoint cycles. So what I'm left with is to show that every cycle can be written as a product of transpositions. Once I prove that, then I'm done. Okay, and the proof in order to show that any cycle can be written as a product of transposition is just given here. right? So any cycle in general, I can write it as I1 to Ik, right? This is a K cycle. How do I obtain this cycle as a result of taking a product of transpositions? Okay, so I1 goes to I2, that's here. What about I2? I2 goes to I1, right?
Yes.
What will the next transposition do to I2?
I2 goes to I.
Exactly, because I2 goes to I1, I1 goes to I3. So therefore, combining these two, we can write that I2 goes to I3 and I1 goes to I2. Okay. Similarly, you can easily verify that again that this side is equal to this. Okay, so that is the proof for this result. Okay, remember this is not a product of disjoint cycles. Okay, result on transposition doesn't say anything about whether the transpositions are disjoint or not. Simply says that any permutation can be written as a product of transpositions. Okay, I hope it is clear. So if I stop here, you may be wondering why there are 15 minutes left. Simply because there is a quiz for you guys today. Right, if you go to the course web page, in this week module of the Moodle, you will be able to find a quiz. The quiz starts at 9:33 a.m. So there's roughly 2 minutes for you guys to open up your Moodle, login, etc., etc. Remember, once you start attempting the quiz, you have exactly 7 minutes. Okay, it's a very odd number, but I thought in order to do those many questions, 7 minutes is enough because I also have to worry about cheating. So I think in a minute's time, you should be able to attempt the quiz. If somebody could confirm that, it would be great. Then I will sort of end this meeting. Okay, you should, I mean, if I think the last time for you to start the quiz, I believe, is 9:40. Okay, so there is a small window within which you should start the quiz, and once you start the quiz, you have about 7 minutes to attempt. Remember, there will be negative marking and different negative markings. Please read the instructions carefully before you start the quiz. Can somebody give me a confirmation if the quiz is working? Oh, think I made a mistake.
Sir, it's not working.
Sir, it is showing the quiz was closed yesterday.
Yes, right, yes. Just give me a second. So try it out now. Okay, I'm waiting for somebody to confirm, then I.
Yes, sir.
It's working?
It is showing attempt quiz now.
Yes,
Okay.
sir. It's
Thank
working.
you. All the best. Ending the meeting. See you on Wednesday. Sorry, Friday.